What if I told you we are on the brink of a new era where interplanetary travel could become as routine as a flight across the globe? In a world where technology is advancing at lightning speed, the idea of traveling to the planets in our solar system is not just science fiction but an impending reality. Imagine boarding a spacecraft and setting a course for Mars, Jupiter, or even the icy depths of Neptune. It's not merely about the destination but the incredible journey and the groundbreaking technology that could take us there. But just how long would it take to reach these distant worlds with the technologies of tomorrow? Buckle up as we delve into the vastness of space to explore the fascinating possibilities of futuristic space travel. By the end of this video, you might find yourself dreaming of your own cosmic adventure, armed with insights that could transform how you view our place in the universe. Imagine embarking on a journey that transcends the boundaries of Earth, venturing into the enigmatic expanses of our solar system. This isn't just a trivial endeavor, but a monumental leap that embodies the spirit of human curiosity and innovation. The solar system beckons with its alluring mysteries and promises of discovery. However, to embark on such an odyssey, we must grapple with various complexities that unfold as we push the limits of our current technology. Consider the sheer distance and immense void that lies between us and the heavenly bodies orbiting our Sun. With each planet posing its own set of challenges, from Mercury's proximity to the Sun to Neptune's icy remoteness, the journey promises not only awe-inspiring vistas, but also formidable tests of our scientific and engineering prowess. Propulsion systems must evolve to propel us further and faster. Communication technology needs to be robust enough to bridge the vast distances, and we must devise life support systems that can sustain human life for years in the harsh environment of space. The questions of transit time, energy requirements, and safety are paramount as we plan for interplanetary sojourns. As we set the stage for this exploration, we delve into the nuances of space travel, examining how current and emerging technologies could shorten travel times, address environmental challenges, and make interplanetary travel a tangible reality. Our journey through space is not only one of distance, but also a profound exploration of human potential and the indomitable will to reach new frontiers. Mercury, the enigmatic planet closest to the Sun, presents a unique set of challenges for any mission aiming to explore its surface. Unlike its earthly neighbors, Mercury's proximity to the Sun makes it a formidable destination. Imagine a journey where the Sun's intense gravitational pull constantly tugs at your spacecraft, demanding precise calculations and expert navigation to ensure a successful arrival. The spacecraft must be designed to withstand not only the scorching temperatures that can reach up to 800 degrees Fahrenheit, but also the frigid conditions of the planet's night side that plummet far below freezing. To embark on this mission, a spacecraft using current technology would take approximately 3 months. Making use of gravity assists from Earth or Venus to effectively enter Mercury's orbit. The route to Mercury is not a straightforward one, as the intricate dance of orbital dynamics requires multiple trajectory adjustments to counteract the strong solar gravitational influence. This approach not only saves fuel but also minimizes travel time, crucial elements in the success of such a high-stakes mission. As we continue our journey through the solar system, each planet's journey time reveals the intricacies and ingenuity needed to overcome the challenges posed by our celestial neighbors. Traveling to Mercury means confronting an array of daunting technical and environmental challenges that truly test the limits of our current spacefaring capabilities. The first and foremost obstacle is Mercury's extreme temperatures, fluctuating dramatically between its blistering days and frigid nights. Imagine a spacecraft needing to endure the harsh inferno of a sun-facing side, where temperatures can soar to nearly 800 degrees Fahrenheit, only to transition to the icy night, where temperatures plunge to -300. Such conditions demand cutting-edge thermal protection systems to ensure that both the equipment and any potential crew remain safe. But temperature is just the tip of the iceberg. The proximity of Mercury to the Sun creates a gravitational pull that requires meticulous propulsion adjustments. Any mission bound for Mercury must be equipped with advanced propulsion technologies powerful and agile enough to navigate the intense gravitational forces at play. While gravity assists from nearby planets like Earth or Venus can help manage these forces, the journey still requires precise trajectory control and robust propulsion systems to accommodate the constant solar tug and make necessary course corrections. These challenges highlight the necessity for durable materials that can withstand severe temperature shifts and engineering prowess in designing propulsion systems that can operate efficiently under extreme conditions. As we push the boundaries of what is possible with current technology, each step toward Mercury becomes a testament to human ingenuity and resilience in the face of the universe's formidable obstacles. As we ponder these challenges, we prepare to face the adventures that await us with each planet in this solar odyssey. Venus stands as Earth's nearest planetary neighbor, a bright beacon in our night sky, and a natural target for space exploration. The journey to Venus is notably shorter and more direct than to most other planets, thanks to its relative proximity. With current technology, a spacecraft journey to Venus would take approximately 3 to 5 months, depending on the planetary alignment and the specific trajectory chosen. This transit time positions Venus as more accessible compared to the distant giants of the solar system, making it an attractive option for future missions. The path to Venus often involves a Hohmann transfer orbit, an efficient route that takes advantage of minimal energy expenditure to traverse the cosmic distance. This method utilizes the gravitational pull of the Earth and Venus to propel the spacecraft, curving its path in a gentle arc between the two planets. The closeness of Venus not only reduces journey time but also simplifies mission planning, allowing for more frequent launch windows and potentially quicker returns. As we plot a course for Venus, this journey highlights how proximity can play a pivotal role in interplanetary travel, setting the stage for deeper explorations into the mysteries of our neighboring worlds. Venus may be tantalizingly close, but its environment presents formidable challenges that make any mission there a test of technology and endurance. Picture a planet enshrouded in a thick, swirling atmosphere composed mainly of carbon dioxide, with clouds of sulfuric acid blanketing its skies. This thick atmosphere creates an immense surface pressure, over 90 times that of Earth's, which is equivalent to being nearly 1,000 meters underwater in the ocean. The crushing pressure alone necessitates spacecraft and equipment that can withstand conditions that are beyond anything we encounter here on Earth. But the challenges don't stop there. Venus is a world of searing heat, with average surface temperatures reaching a blistering 860 degrees Fahrenheit, hot enough to melt lead. This intense heat is a result of a runaway greenhouse effect, making the planet hotter than Mercury despite being farther from the Sun. Any mission to Venus must contend with the challenge of developing technologies that can operate in such extreme heat, requiring cutting-edge thermal protection and cooling systems to shield equipment and potentially humans from the relentless furnace-like conditions. Navigating this hostile world means crafting innovative solutions to overcome the thick veil of clouds that obscure its surface from view. Advanced radar and imaging technologies become crucial for mapping and studying this enigmatic planet, as traditional optical systems are rendered ineffective by the thick, acidic atmosphere. As we contemplate the challenges of Venus, we are reminded that while it is our nearest neighbor, it remains an alien and formidable world, demanding the highest levels of innovation and resilience to unlock its secrets. Exploring space begins right at home with Earth, our very own blue planet. Understanding Earth serves as the essential starting point for any journey into the cosmos. It acts as the baseline from which we measure all other celestial bodies. By comprehending Earth's atmosphere, gravity, and surface conditions, scientists can draw comparisons and contrasts when planning missions to other worlds. This deep understanding is crucial as it allows us to anticipate and solve the myriad of challenges we face in space exploration. But what makes Earth such a critical reference point? Firstly, our planet's diverse ecosystems and climates provide a rich source of data, helping us to develop technologies that can operate under different conditions, from extreme cold to intense heat. This adaptability is vital when designing spacecrafts and suits for the varied environments of planets like Mars or Venus. Moreover, Earth is our primary testing ground for life support systems, which are essential for long-duration missions. These systems must be rigorously tested to ensure they can effectively recycle air and water, manage waste, and provide a habitable environment for astronauts millions of miles away from home. The human factors are equally important. Earth's gravitational field shapes how we adapt to the microgravity environments of space. Understanding the physiological and psychological effects of long-term space travel begins with studying how our bodies respond to different conditions on Earth. This includes everything from muscle and bone density loss to mental health challenges astronauts may face when isolated for long periods. Harnessing this knowledge allows us to prepare crews for the demands of interplanetary travel. As we look to the stars, Earth remains our most valuable ally, teaching us how to protect and sustain life beyond its boundaries. With each mission, we carry the lessons of Earth into the space, ensuring that our journey into the solar system is not just about reaching distant planets, but also about understanding the fundamental principles that govern our existence. The time it would take to travel to Mars, often referred to as the Red Planet, is influenced by several factors, primarily the alignment of the planets and the technological capabilities at our disposal. With current technology, the journey to Mars is estimated to take approximately 6 to 9 months. This time frame depends significantly on the opportune periods when Earth and Mars are properly aligned, known as launch windows. These windows occur roughly every 26 months when the planet's orbits bring them closest together, minimizing travel distance and energy consumption. During these windows, spacecraft can take advantage of what's known as a Hohmann transfer orbit, which is an efficient route that allows a spacecraft to use the least fuel possible. This trajectory exploits the gravitational fields of both planets, creating a smooth yet calculated path that forms an elliptical orbit around the Sun. Utilizing this method, space agencies aim to optimize the journey by reducing both travel time and resource requirements, making these missions more feasible. While the duration of the journey might seem long, advancements in propulsion technology, such as ion thrusters or even theoretical nuclear thermal engines, hold the potential to significantly reduce the travel time in the future. As we look towards the future of space exploration, refining these technologies is crucial in shortening the duration and making round-trip missions to Mars more practical. Each step taken towards the Red Planet not only brings us closer to discovering its secrets, but also pushes the boundaries of our understanding and capabilities in space travel. As we ponder the journey ahead, Mars stands as a testament to what lies on the horizon for human exploration in our solar system. The logistics of planning a mission to Mars involve a delicate balance of timing, resources, and human considerations. At the heart of these plans are the launch windows, critical periods that dictate when a spacecraft can be sent most efficiently. These windows, opening every 26 months, are determined by the orbits of Earth and Mars when they are closest, reducing travel time and energy expenditure. Timing is everything, as missing a window could delay a mission by more than 2 years. During the planning phase, engineers calculate the optimal trajectory using a Hohmann transfer orbit, which requires precise alignment of the planets. This calculation ensures that the spacecraft can reach Mars with minimal fuel usage while maintaining a viable speed. But reaching Mars is only half the journey. A return voyage must be carefully orchestrated, with resources like fuel and life support systems meticulously accounted for. Planners must consider the potential for in situ resource utilization, harvesting materials from Mars to produce fuel for the return trip, a revolutionary concept that could significantly lower costs and increase feasibility. Human factors are also pivotal in mission planning. Prolonged space travel presents challenges such as psychological impacts, muscle atrophy, and radiation exposure, all of which require robust mitigation strategies to safeguard astronaut health. Habitation modules need to be designed to withstand long-duration missions, providing comfort and safety in an environment where isolation and time away from Earth weigh heavily on crew well-being. By integrating advanced medical systems, exercise equipment, and radiation shielding, mission planners create an ecosystem that supports the physical and mental health of the crew. This intricate planning transforms the once daunting ambition of a Mars mission into a feasible endeavor, bringing us one step closer to the realization of human exploration on another planet. The journey to Jupiter, the largest planet in our solar system, represents one of the most ambitious challenges in space exploration. Due to its significant distance from Earth, the journey to Jupiter typically takes around 6 years to complete using current technology. This extended travel time is influenced by several critical factors, including the vast distance that separates us from this gas giant and its enormous gravitational field. Jupiter's gravitational pull is extraordinarily powerful, a characteristic that can complicate mission planning but also provide opportunities for gravitational assists to accelerate spacecraft and conserve fuel. These assists involve using the gravitational field of another celestial body, like a planet or moon, to increase a spacecraft's speed and alter its trajectory towards its target. To navigate these complexities, space agencies meticulously plan the spacecraft's trajectory, ensuring that it takes advantage of potential flybys of other planets, like Venus or Earth, to pick up speed and reduce the energy required to reach Jupiter. During this journey, the spacecraft must traverse through the asteroid belt, a region filled with countless rocky bodies orbiting between Mars and Jupiter. Although the likelihood of collision is minimal due to the vast distances between these bodies, careful trajectory plotting is essential to avoid potential obstacles. Once in Jupiter's vicinity, the mission faces the challenge of entering and maintaining orbit around the planet. This requires precisely calibrated maneuvers to counter the immense gravitational forces and ensure successful insertion into orbit for exploration. The intricate planning and execution needed for a successful mission to Jupiter not only underscore the complexity of such endeavors, but also highlight the remarkable potential for discovery among its many moons and the mysteries of its swirling atmosphere. When considering a journey to Jupiter, one must grapple with the formidable radiation challenges posed by its intense magnetic field. Jupiter's magnetic field is the strongest in our solar system, creating a radiation environment far more severe than anything we experience on Earth. This radiation, composed of energetic particles trapped by the magnetic field, forms intense radiation belts similar to Earth's Van Allen belts but vastly more powerful. The radiation levels within these belts can damage or even destroy spacecraft electronics, posing a significant risk to any mission. To withstand such harsh conditions, spacecraft must be meticulously designed with advanced radiation shielding to protect sensitive instruments and systems. The development of such shielding requires innovative materials that can absorb or deflect high-energy particles, ensuring the spacecraft remains operational throughout its mission. Moreover, the planning process must take into account these radiation hazards, dictating the trajectory and the duration of time a spacecraft spends near the planet. Strategically minimizing time within the radiation belts is crucial to prevent undue exposure. In some missions, a strategy known as the Galileo technique, might be employed, which involves looping the spacecraft into an orbit that spends minimal time in the most hazardous regions. By balancing these engineering and planning measures, we can ensure that missions to Jupiter are both safe and productive, paving the way for groundbreaking discoveries in the planet's atmosphere and its intriguing collection of moons. These challenges not only test the technological limits of our current capabilities, but also drive innovation, pushing us to develop robust systems capable of enduring Jupiter's harsh radiation and expanding our understanding of this gas giant. The estimated time to travel to Saturn, the majestic ringed giant, is approximately 7 years using current space travel technology. This journey is significantly influenced by the substantial distance between Earth and Saturn, which averages around 890 million miles, and the intricate dance of its iconic rings. This enormous gap necessitates a carefully calculated path, often involving gravity assists from inner planets like Earth or Venus to build the necessary velocity while optimizing fuel efficiency. Just as with journeys to other distant planets, a mission to Saturn must consider the optimal launch windows when planetary alignments allow for the most efficient route, often utilizing a Hohmann transfer orbit. Unlike more straightforward missions within the inner solar system, the path to Saturn involves several complex maneuvers to avoid potential obstacles, including navigating through or around its heralded ring system. These rings, composed of countless particles ranging from tiny specks of dust to sizable chunks of ice and rock, create a mesmerizing yet challenging environment for any spacecraft. The carefully plotted trajectory must skim the edges of the ring system to allow for scientific exploration without risking collision. This not only extends the travel time, but demands precise navigation and engineering ingenuity to ensure a successful and safe arrival. As we contemplate the voyage to Saturn, the journey represents both a logistical and technological feat, promising vast opportunities for discovery among its moons and the wonders encircling this gaseous giant. Navigating the intricate maze of Saturn's rings presents a unique challenge that requires precise precision and advanced technology. Imagine a spacecraft approaching this iconic planet, where the stunning spectacle of its rings, composed of ice, dust, and rocky particles, spans billions of square miles. While the rings are a breathtaking sight, they are also a potential hazard for any mission. The particles within the rings vary greatly in size, some as small as a grain of sand and others as large as a house, each orbiting Saturn at high speeds. These conditions demand that spacecraft systems are equipped with sophisticated sensors and tools to map and track ring particles and ensure safe passage. The risk of collision with these particles means that engineers must meticulously plan and simulate the spacecraft's trajectory to avoid the densest areas. This involves plotting a course that takes the craft through the gaps between rings, a maneuver often compared to threading a needle. Even a small miscalculation could endanger a mission by damaging the spacecraft or altering its path. Innovative navigation systems capable of real-time adjustments are crucial, allowing the craft to react to unexpected obstacles or changes in the ring's dynamics. Furthermore, the gravitational influence of Saturn and its moons can impact the spacecraft's path, requiring complex calculations to maintain stability and ensure mission safety. By addressing these navigational challenges, we not only unlock the potential for groundbreaking exploration of Saturn and its companion moons, but also continue to extend the boundaries of what can be achieved in space exploration. Reaching Uranus, an ice giant distinct with its pale blue-green color, involves a journey far more extended than those to the inner planets. This remote world sits at an average distance of over 1,800,000,000 miles from Earth, resulting in a journey time of approximately 12 to 15 years using current spacecraft technology. This significant duration reflects not only the sheer distance but also the slow, careful planning needed to ensure a successful mission. Unlike the inner planets, which benefit from more frequent and direct launch windows due to their closer proximity, missions to Uranus must be meticulously coordinated to take advantage of rare planetary alignments. These alignments, crucial for incorporating gravity, assists from other planets like Jupiter or Saturn, can drastically reduce the energy and fuel required for the journey, albeit at the cost of longer transit times. As we plot a trajectory towards Uranus, we must consider the spacecraft's path through this distant frontier, navigating the vast expanse of space with precision. These extended missions demand robust and durable spacecraft systems designed to withstand the long years of travel and the harsh conditions of deep space. The challenge is not merely reaching Uranus, but maintaining spacecraft functionality and communication over such an extended period, necessitating advancements in long-term power generation and onboard system reliability. This journey underscores the need for innovation and patience in our quest to explore the far reaches of our solar system, promising rich opportunities for discovery among Uranus's unique atmosphere and complex system of rings and moons. Uranus, with its icy atmosphere and remote location, presents an array of unique challenges that test the resilience of both technology and engineering. Imagine a spacecraft journeying through the freezing void of space to reach Uranus, a planet that basks in the dim glow of the distant sun, so far removed that it receives just a fraction of the sunlight we enjoy on Earth. The temperature on Uranus plunges to an astonishingly frigid -371 degrees Fahrenheit, making it one of the coldest planets in our solar system. High-performance thermal insulation becomes crucial to protect the spacecraft's instruments and any potential crew from these extreme conditions. This insulation must be sophisticated enough to prevent heat loss and keep essential systems operational throughout the mission. Additionally, the vast distance from Earth poses significant power constraints. Traditional solar panels, the primary energy source for many space missions, become less effective this far from the Sun. This necessitates the development of alternative power solutions, such as nuclear power systems or advanced battery technologies, to ensure a steady energy supply for propulsion, life support, and scientific instruments. Maintaining efficient power generation and storage is imperative, as any failure could jeopardize the mission's success and the survival of the crew. The cold environment also impacts the design of the spacecraft itself, requiring materials that remain flexible and durable in low temperatures. These materials must withstand not only the cold but also radiation and micrometeoroid impacts prevalent in space. As we contemplate the challenges of reaching Uranus, mastering these technological and environmental hurdles becomes a testament to human ingenuity and determination, paving the way for future explorations into the depths of our solar system. Neptune, the most distant planet in our solar system, presents a formidable challenge when it comes to interplanetary travel. The journey to this icy giant, which sits more than 2,700,000,000 miles away from Earth, is a significant undertaking that pushes the limits of current space travel technology. Estimated to take approximately 12 to 15 years using current propulsion systems, this mission is not just about covering vast distances, but also about managing the prolonged duration of space travel. The immense distance between Earth and Neptune means that mission planners must meticulously map out the spacecraft's trajectory, often relying on gravity assists from neighboring planets like Jupiter or Saturn to gain the necessary speed. These assists are crucial to conserving fuel and ensuring the spacecraft maintains its course over the lengthy journey. The extended travel time to Neptune necessitates advancements in spacecraft durability and life support systems, ensuring that all onboard equipment remains functional over the many years required to reach this distant world. Additionally, maintaining communication across such vast expanses of space presents its own set of challenges, requiring sophisticated technology to ensure consistent and reliable data transmission back to Earth. As we explore the possibility of reaching Neptune, we recognize that it demands both technological innovation and a deep understanding of the challenges posed by such a remote and isolated environment, ushering in a new era of exploration at the furthest frontiers of our solar system. Operating in the distant and isolated region of Neptune presents significant challenges that stretch the boundaries of our current technological and logistical capabilities. Imagine a spacecraft millions of miles from Earth, navigating the vast emptiness of space with only the distant glow of this icy planet as its guide. The isolation is profound, with the sheer distance creating a communication lag that can extend to several hours for a signal to travel between Earth and the spacecraft. This delay means that real-time communication is virtually impossible, necessitating autonomous systems capable of making critical decisions without immediate human intervention. The spacecraft must be equipped with advanced artificial intelligence and robust autonomous systems to handle unexpected situations and ensure mission success. Furthermore, the remoteness of Neptune significantly hampers potential support from Earth. In the event of a malfunction or emergency, the traditional methods of troubleshooting and repair become exceedingly difficult due to the extended lag in communication and the time it would take to send physical aid. This isolation underscores the importance of designing spacecraft with redundancy and durability, ensuring they can operate independently for long durations. The spacecraft systems must be meticulously tested and built to withstand the harsh conditions of deep space, with multiple backup systems in place to address any potential failures. Supplies and fuel need to be carefully managed, as resupply missions are not feasible at such distances. As we prepare for missions to Neptune, overcoming these challenges requires not only cutting-edge technology, but also an innovative approach to mission planning and execution. In this remote and isolated part of the solar system, human ingenuity and resilience are key to unlocking the mysteries that await on Neptune's doorstep. This endeavor not only pushes the frontiers of space exploration, but also expands our understanding of what's achievable in the face of the universe's vast and enigmatic expanse. Reaching Pluto, the most renowned of the dwarf planets in our solar system, represents one of the most ambitious journeys humankind can undertake. Situated over 3 billion miles from Earth, Pluto's remote location poses unique challenges that demand both careful planning and technological innovation. With current technology, the time it takes to reach Pluto is approximately 9.5 years, as demonstrated by NASA, a New Horizons mission. This journey is heavily influenced by the spacecraft's ability to perform gravity assists, a crucial technique that involves swinging around other planets to increase speed and conserve fuel. The New Horizons mission used a gravity assist from Jupiter, which significantly shortened travel time, highlighting the importance of such maneuvers in long-distance space travel. Pluto's classification as a dwarf planet adds another layer of complexity, as its small size means it exerts a relatively weak gravitational pull compared to larger planets. This factor requires precise trajectory planning to ensure the spacecraft arrives accurately and can perform scientific observations effectively. The lengthy journey across the vast expanse of space also necessitates advancements in spacecraft durability, ensuring that all systems remain operational over many years. As we contemplate a mission to Pluto, we are reminded of the challenges and opportunities presented by exploring the outer edges of our solar system, where the combination of distance, isolation, and the need for robust technology shape the future of space exploration. Exploring Pluto offers a treasure trove of scientific opportunities, as it remains one of the most enigmatic bodies in our solar system. Picture a world where the sky is a deep blue and the surface is covered in exotic ices, revealing secrets locked away in its ancient landscape. Studying Pluto's atmosphere alone opens a window into understanding how atmospheres evolve in extreme environments. Despite its distance from the Sun, Pluto has a thin atmosphere composed mostly of nitrogen, with traces of methane and carbon monoxide. This unique composition provides a natural laboratory to study atmospheric processes in incredibly cold conditions, shedding light on seasonal changes and how solar winds interact with distant celestial atmospheres. Pluto's surface presents another rich avenue for discovery. The diverse terrain with its vast plains, towering mountains, and icy volcanoes tells a story of geological activity that has puzzled scientists. By examining surface compositions, researchers can gather insights into the planet's geologic history and internal structure. This offers clues into the dynamics of icy bodies and the processes that have shaped them over billions of years. Additionally, the discovery of Pluto's complex system of moons presents further scientific intrigue. Investigating these moons can enhance our understanding of satellite dynamics and the interactions between celestial bodies in a multi-moon system. Each moon adds a layer of complexity and potential for groundbreaking research, contributing to a more comprehensive understanding of how similar systems might behave across the universe. Through these pursuits, a mission to Pluto not only deepens our knowledge of this distant dwarf planet, but also unlocks broader cosmic mysteries, enriching our grasp of planetary science and the diversity of celestial environments. Exploring the current and emerging technologies that could reduce travel time to the planets, we find ourselves on the cusp of a revolutionary shift in space travel. At the forefront of this transformation are advanced propulsion systems that promise to make interplanetary journeys faster and more efficient than ever before. Traditional chemical rockets, which have been the cornerstone of space exploration, are being gradually supplemented by innovative propulsion methods that offer greater speeds and reduced travel times. One such promising technology is ion propulsion, which uses electricity to accelerate ions, creating a thrust that, while initially weaker than traditional rockets, can sustain its propulsion for extended durations. This allows spacecraft to reach higher speeds over time, significantly cutting down the years it would take to reach distant planets. Furthermore, the development of nuclear thermal propulsion is gaining traction. This technology, leveraging the incredible energy density of nuclear reactions, could propel spacecraft faster by heating propellant to extremely high temperatures, providing a powerful thrust capable of reducing travel times to Mars to weeks instead of months. Looking beyond the near-term innovations, concepts such as solar sails harness the momentum of photons emitted by the sun to propel ships. While still in their early stages, these sails could provide a nearly inexhaustible source of propulsion for deep space missions, allowing for sustained, fuel-efficient travel across the solar system. The vision of interplanetary travel is further bolstered by emerging ideas in fusion propulsion, a technology that aims to harness the same energy processes powering the sun to push spacecraft to unprecedented speeds. Though still in the experimental phase, fusion holds the potential to enable humanity to reach the outer planets in a matter of years, dramatically altering the landscape of space exploration. As we stand at the threshold of this new era, these advanced propulsion systems signify our relentless pursuit of faster and more sustainable means to explore the cosmos, and they hold the key to opening the universe's vast, uncharted territories to human exploration. Discussing the human factors involved in long-duration space travel, we encounter a realm where technology and human resilience must intricately intertwine to ensure success. One of the foremost considerations is life support, as it forms the backbone of any mission intended to carry humans through the vastness of space. Advanced life support systems must efficiently recycle air and water while managing waste to create a self-sustaining environment. These systems mimic Earth's natural balance, requiring a delicate blend of engineering ingenuity and biological processes to maintain a habitable space for astronauts over extended periods. Health is another pivotal aspect where the microgravity environment of space presents unique challenges, as the lack of gravity can lead to muscle atrophy and bone density loss, conditions that necessitate rigorous exercise regimes tailored to space conditions. Exercise equipment must be compact yet effective, ensuring astronauts maintain their physical fitness despite the confines of a spacecraft. Additionally, the isolation and confinement inherent in long-duration missions can exert significant psychological pressure on the crew. Maintaining mental well-being relies on a combination of communication with loved ones back on Earth, recreational activities, and design elements within the habitat to create a sense of home. The psychological resilience of astronauts is as critical as their physical health, with strategies in place to help them cope with the stresses of isolation, limited social interactions, and the ever-present risks of space travel. As we advance in our quest for deep space exploration, addressing these human factors becomes crucial, paving the way for missions that not only survive but thrive amid the stars. Speculating on future missions and technological innovations that could make planetary travel faster and more efficient, we stand on the brink of a transformative era. Engineers and visionaries are exploring concepts that once seemed the realm of pure science fiction. Imagine the potential of spacecraft equipped with warp drives, leveraging theoretical physics to bend space-time and cut interplanetary distances drastically. While still speculative, advancements in our understanding of quantum mechanics and general relativity could make them a reality. Alongside these thrilling possibilities, more immediate innovations are on the horizon. Space agencies are actively developing reusable spacecraft, akin to the current efforts with reusable rockets, to significantly reduce costs and launch preparation times. These reusable vehicles could facilitate a continuous human presence in space, with regular commutes between Earth and other planets becoming commonplace. Another realm of innovation lies in the realm of on-demand manufacturing. Picture a future where spacecraft are equipped with advanced 3D printers capable of producing tools and components during the mission, reducing the need for exhaustive inventories and allowing quick adaptation to unforeseen challenges. This technology not only streamlines missions but also enhances the flexibility crucial for long-duration journeys. In situ resource utilization is yet another transformative concept. Envision missions utilizing local resources from celestial bodies, such as extracting water from Mars or the Moon to produce oxygen and hydrogen fuel. This approach unlocks possibilities for extended stays on other planets, reducing dependency on Earth-supplied materials and paving the way for sustained exploration. The evolution of artificial intelligence holds promising prospects for mission efficiency, with AI managing complex tasks autonomously, optimizing navigation, and performing real-time data analysis to enhance mission safety and productivity. As we dream of venturing beyond our planetary neighborhood, these innovations stand as beacons of possibility, indicating a future where interplanetary travel becomes a seamless reality driven by ingenuity and the human spirit's relentless pursuit of exploration. Return journeys are a critical aspect of interplanetary travel, requiring meticulous planning to ensure the safe return of spacecraft and crew to Earth. One of the most significant challenges involves managing the fuel requirements for these long trips. A spacecraft departing from a distant planet must have enough fuel to break free from the planet's gravity, travel back through space, and safely enter Earth's atmosphere upon return. This often means missions must carry additional fuel reserves, or even better, leverage in situ resource utilization to create fuel from materials found on the surface of other planets. Timing also plays a pivotal role in planning return journeys. Like the journey out, the return must be carefully timed to coincide with optimal planetary alignments, minimizing travel time and conserving fuel. Missing this window could result in a prolonged journey back, adding months or even years to the mission duration. Additionally, planners must account for Earth re-entry timing to ensure that the spacecraft arrives when conditions are favorable. Safety is paramount throughout this process, encompassing not only the physical integrity of the spacecraft but also the well-being of its crew. The return trip presents unique psychological and physiological challenges, as astronauts must navigate the stress of leaving a distant world and the anticipation of returning home. Designing spacecraft with robust life support systems and redundancies ensures that they can withstand the long journey and potential emergencies. Additionally, communication with Earth must be maintained, allowing for regular updates and support from mission control. Successful return journeys are a testament to our ability to plan and execute complex missions, marking the full circle of interplanetary exploration as we not only reach out to distant worlds but also safely guide our explorers back home. As we refine the intricacies of return journeys, we lay the groundwork for a sustainable presence in space, ensuring that exploration is not a one-way ticket but an enriching round trip into the cosmos. Planetary alignment and timing play a crucial role in determining the duration and success of space missions. Imagine the solar system as a vast cosmic dance floor, where each planet moves around the Sun in its own unique path and speed. These paths occasionally bring the planets into specific alignments, creating ideal conditions known as launch windows for space travel. When planets align favorably, these windows allow spacecraft to take the most efficient routes, minimizing the energy needed to reach their destinations. This alignment not only shortens travel time, but also reduces the overall mission cost by conserving fuel. For instance, when planning a journey to Mars, these launch windows occur approximately every 26 months when Earth and Mars are optimally aligned, allowing spacecraft to follow a Hohmann transfer orbit. This path takes advantage of the planet's gravitational fields, enabling a smooth and energy-efficient journey. Timing is everything in these missions, as missing a launch window could delay a mission by years and necessitate the recalibration of trajectories. Mission planners meticulously calculate trajectories and adjust spacecraft launch dates to coincide with these brief windows to ensure optimal conditions. They must also consider the varying speeds and orbits of the planets, which influence the duration of the travel. By understanding and harnessing these alignments, we not only increase the feasibility of interplanetary travel, but also gain insights into the celestial mechanics that govern our solar system. As we look to the stars, acknowledging the significance of planetary alignment and timing becomes a testament to our ability to navigate the cosmic dance that guides us through this great interstellar expanse. Interplanetary communication is a fundamental aspect of space exploration that presents considerable challenges, especially when maintaining a link between spacecraft and Earth over the vast distances of the solar system. Imagine a spacecraft millions of miles away, needing to send data back home, where any signal takes several minutes or even hours to reach Earth due to the sheer distance. This delay, known as the communication lag, complicates real-time operations and necessitates planning for autonomous systems that can function effectively without constant input from mission control. The technology required to bridge these cosmic gaps is truly remarkable. At the heart of this communication network are the deep space network antennas, enormous parabolic dishes carefully spaced across the globe to maintain continuous contact with space missions. These antennas are equipped to send and receive radio signals which travel at the speed of light, yet still require time to cross the immense expanses of space. Additionally, advancements in laser communication or optical communication hold promising potential to enhance data transmission rates. By using lasers instead of traditional radio waves, these systems can deliver much larger volumes of data over long distances with greater speed and accuracy. However, this technology requires precise aiming and stability, since even the smallest misalignment can disrupt communication. As spacecraft venture deeper into the solar system, maintaining a strong connection becomes increasingly challenging due to the weakening signal and potential interference from cosmic radiation and planetary bodies. To ensure robust interplanetary communication, spacecraft must be equipped with advanced transmission and reception systems capable of handling a wide range of frequencies and atmospheric conditions. As we continue to push the boundaries of space exploration, interplanetary communication technology remains a critical component, ensuring that we remain connected to our distant exploratory outposts and can safely guide them through the uncharted territories of our celestial neighborhood. Spacecraft design and durability are pivotal when venturing beyond our planet on interplanetary journeys, demanding advanced engineering solutions to withstand the robust conditions of space travel. Imagine a spacecraft hurtling through the vast void, facing challenges such as extreme temperatures, intense radiation, micrometeoroid impacts, and prolonged isolation. These adversities require that every component of a spacecraft be meticulously crafted and rigorously tested to ensure it can endure the voyage while safeguarding its precious cargo, often human explorers or delicate scientific instruments. The outer shell of the spacecraft acts as its first line of defense, constructed from materials that are not only lightweight to conserve fuel, but also exceptionally strong and resistant to the wear and tear of space. These materials often include advanced composites and alloys designed to maintain structural integrity under severe conditions, to protect against temperature swings ranging from the scorching heat when facing the sun to the frigid cold on the dark side. Spacecraft are fitted with thermal control systems. These systems use insulation, heat radiators, and sometimes active cooling methods to maintain a stable internal temperature, ensuring that equipment operates optimally. Radiation is another formidable challenge, with levels far exceeding those encountered on Earth, especially when traveling near planets with strong magnetic fields like Jupiter. Spacecraft are designed with specialized shielding to block harmful radiation, often using layers of dense materials to absorb or deflect high-energy particles. Internally, spacecraft must accommodate human needs for long-duration missions. This includes designing living quarters that are comfortable yet compact, balancing the need for privacy with the constraints of limited space. Life support systems are integrated to manage air, water, and waste, creating a self-sustaining environment. Redundancy is key, with backup systems in place to handle potential failures quickly and efficiently. The design must also consider the psychological well-being of astronauts, incorporating elements that promote mental health, such as natural lighting and recreational spaces. As we continue to advance our exploration of the solar system, these design considerations ensure that spacecraft are not only capable of reaching distant planets, but also returning safely, embodying the spirit of resilience and ingenuity that drives human exploration. The role of artificial intelligence in space exploration has become increasingly vital as we push the boundaries of what is possible in our quest to explore other planets. Picture a future where AI acts as the backbone of mission planning, handling complex calculations and logistical challenges with unmatched precision. The sheer distance and isolation of interplanetary travel demand that missions operate efficiently and safely, necessitating a level of computational power and decision-making that AI is uniquely equipped to provide. In the planning phase, AI systems analyze vast amounts of data to determine the most optimal launch windows and trajectories, ensuring that spacecraft can reach their destinations with maximum fuel efficiency and minimal risk. These systems continuously update and refine mission parameters, using real-time data and predictive modeling to anticipate and mitigate potential challenges. Once in space, AI systems become the navigators, adeptly managing the myriad tasks required to keep a spacecraft on course. They monitor environmental conditions, adjust trajectories in response to unexpected events, and ensure that the spacecraft systems are functioning optimally. This level of automation is crucial when communication delays with Earth make real-time human intervention impossible. Moreover, AI's ability to process and analyze data quickly and accurately enables remote scientific exploration. Onboard AI systems can identify and prioritize targets for observation, conduct initial analyses, and even manage experiments, freeing up human astronauts to focus on other critical tasks. This capability is especially important in environments where human presence may be limited or impossible. As we continue to explore the solar system, AI will play a pivotal role in optimizing missions, improving safety, and expanding the scope of what we can achieve. By harnessing the power of AI, we not only enhance our capacity for interplanetary travel, but also lay the groundwork for more ambitious missions that drive us deeper into the cosmos. As we conclude our thrilling journey through the solar system, let's reflect on the awe-inspiring complexity and endless excitement that interplanetary travel brings. From the scorching heat of Mercury to the icy depths of Neptune, each planet presents unique challenges and opportunities that push the boundaries of our technology and imagination. We've explored the exceptional advancements in propulsion systems, the critical role of artificial intelligence, and the meticulous planning required for safe and efficient space travel. Through confronting the hostile environments of planets like Venus and Mars, we've seen how human resilience and ingenuity can transform seemingly impossible dreams into tangible realities. The pursuit of understanding our place in the universe opens a world of possibilities, encouraging us to envision a future where space travel is an integral part of humanity's journey. As we continue to unravel the mysteries of our cosmic neighborhood, it's vital to engage with these questions. What lies beyond the horizon for space exploration? How might our ambitions shape the next era of discovery? We invite you to share your thoughts on these exciting possibilities and your aspirations for exploring the cosmos. What planets would you want to visit, and what technologies do you think will redefine our path to the stars? Join this vibrant conversation and dream with us as we imagine new frontiers. If you enjoyed this exploration as much as we did in presenting it, don't forget to like this video, subscribe to our channel, and hit the notification bell to stay updated on all things futuristic and extraordinary. Together, let's keep reaching for the stars.